Welcome to the Explainer. Today, we are literally strapping in for a high-speed descent through our planet's incredibly vast, deep time history. We're going to cover 4.6 billion years of geological and biological evolution, relying on the rock and fossil records to guide our flight. So, let's get right into it.
Now, I want you to imagine something for a second. If Earth's entire 4.6 billion year history was squashed down into a single 24-hour day, what time do you think humans finally showed up? Hold on to your guess. We'll answer it at the very end, but I promise you, the sheer scale of the time we are about to explore is absolutely mind-boggling.
All right, here's our holographic flight plan. We'll chart our course through the Hadean and Archean eons, the Proterozoic oxygen revolution, the Paleozoic evolutionary explosion, the Mesozoic age of reptiles, and finally, the Cenozoic era of mammals and humans. Section 1. The Hadean and Archean eons. Chaos, cooling, and the first sparks of life. We're kicking things off 4.5 billion years ago in the Hadean eon, and it's named quite appropriately after Hades, the Greek god of the underworld, because back then, Earth was essentially this chaotic, molten ball of lava just floating in space. Over hundreds of millions of years, the planet slowly transitioned from a molten hellscape to a cooling crust. By 3.5 billion years ago, we see the very first robust fossil evidence, proving that this cooling rock had actually become capable of supporting life. But hey, before life could even think about taking hold, Earth suffered a massive cosmic collision. It's called the giant impact hypothesis, and it explains the origin of our moon. Basically, a Mars-sized body crashed right into the early molten Earth. The violent impact scattered debris into orbit, and the lower density splatter eventually coalesced to form the moon. This perfectly explains why Earth and the moon have nearly identical isotopic and chemical compositions. It's literally a piece of us. And things absolutely did not calm down quickly. Between 4.1 and 3.8 billion years ago, we had the Late Heavy Bombardment. Gravitational disturbances out in the outer solar system sent a secondary spike of unstable asteroids and comets pummeling into the inner planets. This bombardment is exactly why our moon is so heavily cratered today. But even cooler, it's a leading theory for how frozen comets originally delivered vital surface water to early Earth. That is just a staggering thought when you look out at our oceans today. So here's the absolutely crucial point. Out of all this violent reducing environment, an atmosphere completely devoid of free oxygen and just choked with methane and carbon dioxide, single-celled cyanobacteria emerged. These photosynthetic microbial mats, known as stromatolites, are preserved as fossils in Australia, dating way back 3.5 billion years. These microscopic pioneers were about to change the chemistry of the entire planet forever. Moving into Section 2, the Proterozoic oxygen revolution, transforming the atmosphere and the continents. Now we're entering an eon defined by massive planetary shifts. The Proterozoic spans an incredible 2 billion years of history. We hit some absolutely major milestones here. The Great Oxygenation Event around 2.4 billion years ago, the formation of the supercontinent Rodinia a billion years ago, and finally, the end of the eon 541 million years ago, which perfectly sets the stage for complex life. You know, it's actually kind of ironic when you compare the Archean and Proterozoic worlds. During the Great Oxygenation Event, cyanobacteria pumped massive amounts of free oxygen into the oceans. This essentially poisoned the existing anaerobic life, meaning the very first mass extinction was literally caused by oxygen. Chemically, though, that oxygen reacted with dissolved iron in the water, causing it to rust and precipitate out. This created the massive banded iron formations, full of hematite and magnetite that we heavily mine for our iron today. As the atmosphere changed, the ground beneath it was shifting too. Driven by plate tectonics, the supercontinent Rodinia came together about a billion years ago. But it's actually the breakup of Rodinia a few hundred million years later that's the real game changer here. As the massive landmass fractured, it created vast, shallow water coastal environments. These sunlit, nutrient-rich coastlines fostered incredible evolutionary breakthroughs. All right, Section 3, Paleozoic, an evolutionary explosion. Life conquers the oceans and the land. We are now in the Phanerozoic eon, a word that literally translates to visible life. And boy, does the rock record suddenly explode with life forms boasting hard shells, teeth, and claws. Tracking our progress, it's a thrilling succession of milestones. The Cambrian explosion kicks things off. By 385 million years ago, fish evolved into the first tetrapods.
Then, by 300 million years ago, towering forests covered the continents, only to violently conclude with the Permian mass extinction 252 million years ago.
Let's zoom in on that Cambrian explosion for a second. The Burgess Shale fossil deposits reveal an ocean teeming with strange, almost alien-looking organisms. We're talking trilobites with the first compound eyes, Opabinia, featuring 5 eyes in this bizarre frontal grappling claw, and Anomalocaris, the massive alpha predator. But most importantly for us, Pichea. It was a small, segmented worm that laid the crucial genetic groundwork as an ancestor to all vertebrates. Yes, including you.
Fast forward to the late Paleozoic, and let's see how the physical world builds on this biological explosion. Tectonic plates crashed together again to form the ultimate supercontinent you've probably heard of, Pangaea. It was surrounded by a single global ocean called Panthalassa. This immense landmass caused the global climate to dry out significantly. And why this matters is that this dry climate gave a massive evolutionary advantage to early reptiles. Why? Because they evolved the amniotic egg, allowing them to finally reproduce on land without needing a body of water for their eggs.
But of course, this era of prosperity couldn't last forever. 96%. That shocking number represents the estimated wipeout of all marine species during the Permian-Triassic extinction, along with 70% of land vertebrates. The leading culprit? Massive flood basalt volcanic eruptions, known as the Siberian Traps. They pumped catastrophic amounts of greenhouse gases into the atmosphere, causing a runaway global warming effect. It was, without a doubt, the closest life on Earth ever came to being completely snuffed out.
Section 4. Mesozoic. Age of reptiles. Dinosaurs rule a shifting world. From the absolute ashes of the worst extinction in history, life rebounded. Surviving lineages rapidly radiated to fill the empty ecosystems. If you look at the timeline, notice how the physical breakup of Pangaea, starting around 210 million years ago, perfectly overlaps with the rapid diversification of dinosaurs. We also see the emergence of early mammals, the first birds like Archaeopteryx, and of course the whole era comes crashing down 66 million years ago. The connection between geology and biology here is just incredible. As the continents of Pangaea drifted apart into isolated islands, biology had to adapt to these separated environments. Archosaurs diversified into pterosaurs in the sky and marine crocodiles in the water. We see isolated evolutionary wonders pop up, like the giant titanosaurian sauropod Argentinosaurus down in South America. We see theropod dinosaurs evolving feathers to become birds, and by the end of the era, beautiful flowering plants called angiosperms totally took over the landscapes. But as we all know, the reign of the dinosaurs comes to a very fiery, very sudden halt. 66 million years ago, the KPG extinction was triggered by a massive asteroid collision. It unleashed a thermal pulse, causing global wildfires and a huge sun-blocking debris cloud. And we know this happened for sure because scientists found a global layer of shocked quartz and iridium, a rare element extremely common in meteorites, forever marking the violent end of the Mesozoic. Which brings us to Section 5, Cenozoic, Mammals and Humans, the rise of warm-blooded dominance. With the giant reptiles wiped off the board, surviving mammals rushed in to fill all those empty ecological niches. Bringing our timeline right up to the present day, you can see the modern Ice Age beginning 2.58 million years ago. But look closely at when Homo sapiens emerged, just 300,000 years ago. Going back to our 24-hour clock from the very beginning of this explainer, if Earth's history was a 24-hour day, human beings don't appear until just a few seconds before midnight. We are literally in the final milliseconds of Earth's deep time club. So honing in on our own story, it all really hinges on climate change in East Africa. As lush jungles shifted into open savannas, our hominid ancestors adapted by shifting from tree-dwelling to bipedalism, meaning walking upright on 2 legs. This allowed for endurance running across the plains. But even more crucially, freeing up their hands allowed these early human ancestors to use tools, which drove the massive evolutionary push for larger brains, complex societies, and eventually the migration of our species across the entire globe. And boom, that brings us right to the modern day, an era many scientists are now calling the Anthropocene, a brand new geological epoch defined entirely by human impact. So, I want to leave you with this final provocative thought. If alien geologists visit Earth millions of years from now, what will our rock layer say about us? When they see the massive mountains of Earth we've moved, the sudden megafauna extinctions we've driven, the massive spike in atmospheric carbon, and the lasting plastics left behind, what story will they read in the stones? Thanks for joining me on this wild 4.6 billion year flight. Keep exploring, and I'll catch you in the next explainer.